Hello, I am Jagadish Mahato. I am an assistant professor in the Department of Physics, Ramakrishna Mission Residential College, Narendrapur, Kolkata, India. Now I am working as a researcher in the Institute of Applied Physics, Technical University, Braunschweig, Germany. Today I shall talk on self-organized endotaxial cobalt disillicide nanowires on silicon 110 surfaces, fabrication and aspect ratio tuning of the nanowire. Before going into my talk, I would like to thank the organizer for giving me an opportunity to present my research work in the third International Conference on Material Science and Nanotechnology. So, what is the importance of self-organized nanostructure growth investigation at semiconductor surfaces? This can be understood if we see what Gordon Moore predicted. Gordon Moore predicted that the number of transistors per square inch on the integrated circuit would double every 18 months. And now we are at a stage, due to the resolution limit of the conventional lithography technique, more number of transistors cannot be fabricated on the integrated circuit by the conventional method. The search for alternative device fabrication technique forces us to take advantage of the self-organized growth method. In the self-organized growth method, we deposit one material onto other at appropriate deposition condition. The deposit material form minimum energy nanostructure on the surfaces. What is needed for the clean contamination-free nanostructure growth on surfaces is a clean environment, because from this table we can see that even if we clean the surface and keep in ambient pressure, then in 10 nanoseconds the surface will be covered by the surrounding gas molecule. But if we keep the clean surface at a pressure of 10 to the power minus 11 millibar in a chamber, then it would take 300 hours for the residual gas molecule to cover the surface. So which is sufficient for the growth investigation and other characterization of the sample. So this type of environment is called ultra high vacuum environment. This is achieved with the help of different type of pumps. This type of environment is created in this MBSTM system with the help of different type of pumps, and we can achieve 10 to the power minus 11 to 10 to the minus 10 millibar pressure. I have used this system for the growth investigation and characterization of the sample. So I deposited cobalt on silicon surface, but the silicon substrate contained native oxide layer. To remove the native oxide layer, we carry out standard thermal cleaning procedure. Initially, we heat the sample at 400 degrees Celsius to increase its conductivity, and then we pass a direct current to heat the silicon substrate at 600 degrees Celsius to degas the silicon substrate. Keep there for 14 hours and then suddenly rise the substrate temperature to 1250 degrees Celsius for 60 seconds. At 1250 degrees Celsius, the oxide layer gets removed from the surface. Then we cool down the substrate temperature to 870 degrees Celsius, keep there for 30 minutes and then slowly cool to room temperature. At 870 degrees Celsius, the top layer surface atoms rearranges themselves to form minimum energy surface. This rearrangement of the top layer atom is called surface reconstruction. Silicon 100 surface undergoes 2 cross 1 reconstruction. Silicon 110 undergoes 16 cross 2, 5 cross 1 reconstruction. Silicon 111 surface undergoes 7 by 7 reconstruction. After cleaning the silicon substrate, we deposit our desired material. We create a beam of flux and direct it onto the substrate. The substrate is kept with a heating arrangement. As soon as the atom falls on the substrate, it rolls around on the surface and forms a minimum energy nanostructure depending on the growth condition. So different type of growth mode can be achieved, but technologically most important is epitaxial growth. In epitaxial growth, the deposit follows the crystallographic orientation of the substrate, but always there is a lattice mismatch between the substrate and the film, so strain builds up on the film or on the nanostructure. Not only the strain, but also the surface free energy plays a vital role. If the surface free energy of the substrate is higher than the sum of the film free energy and interface free energy, then we observe layer by layer growth, and in the reverse situation we observe island growth, and in between the two situation we observe layer plus island growth. So in epitaxial growth, as the deposit follow the substrate crystallographic symmetry and orientation, if we start with 4-fold symmetric substrate silicon 100, we expect to have 4-fold symmetric square type of island on top of it. If we start with silicon 110 2-fold symmetric substrate, then we expect 2-fold symmetric elongated rectangular type of nanostructure on it, and for silicon 111 triangular structure is expected to occur. We have used silicon 110 surface, so this is the STEM image of a clean silicon 110 16x2 reconstructed surface. You can see this is the atomic rows which form a 16x2 reconstructed unit. This is the unit cell of the 16x2 unit. Cleaning the silicon wafer, we deposit cobalt at 600 degrees Celsius. At 600 degrees Celsius, cobalt reacts with the silicon substrate and it forms cobalt disilicide nanowire. This is the STM image of the cobalt silicide nanowire grown silicon 110 surface. You can see elongated along the in-plane 110 crystallographic orientation. As we take line profile across this nanowire, we find that there are two distinct types of nanowire cross-sectional area. One is ridge type facet and other is flat top type of facet present in this different nanowires. So to investigate the different nature of the nanowire cross-section, we carried out cross-sectional transmission electron microscopy measurement, and from the cross-sectional transmission electron microscopy measurement, we also found that our observation, the STM observation, is consistent. We found that there are indeed two distinct types of cross-section present in the nanowire. One is flat top type, A1, 2, and 5 is the flat top type of nanowire cross-section, and 3 and 4 is a ridge type of nanowire. To investigate the two distinct types of nanowire cross-section, we have carried out selected area electron diffraction on this distinct type of nanowire cross-section. So here we show the selected area electron diffraction on the flat top type of nanowire cross-section, and we find a diffraction pattern as shown in here, figure D. So to simulate this diffraction pattern, we have simulated silicon diffraction pattern from the 110 zone axis and for the cobalt disilicide. And when we superimpose these two diffraction patterns from silicon and cobalt disilicide from the same zone axis one top of other, then we observe that the diffraction pattern falls exactly on top of other. This is due to the fact that the lattice mismatch between cobalt disilicide and silicon is only 1.2% at room temperature. So from this observation we can say that for the flat top type of nanowire, the cobalt disilicide is growing along the 110 crystallographic orientation. We carried out selected area electron diffraction from the ridge type of nanowire cross section as shown in here by the dotted rectangle. We find a distinct diffraction pattern with respect to the first. Here we find two distinct types of diffraction pattern. So to simulate this diffraction pattern, we have taken again silicon diffraction pattern from the 110 zone axis, and this is the cobalt disilicide diffraction pattern from the 110 zone axis, and when we superpose it, it matches with the experimentally observed diffraction pattern when we superimpose the cobalt disilicide diffraction pattern rotated 110 degree. So from this we can say that here in this ridge type of nanowire, the cobalt disilicide is growing 110 degree rotated with respect to the 110 crystallographic orientation of the silicon substrate. To investigate even further the interface atomic arrangement, we have carried out here the inverse FFT, and from that we have found that the atomic arrangement following the silicon substrate. So this is same for the both sides of interfaces. So in this case the interface is A type. Carried out the same for the this type of nanowire cross-section interface, then we found that the silicon atomic rows are rotated 110 degree. So this is a case of a B type of interface formation. So in this type of nanowire, the interface is B type. Carried out compositional mapping using energy filter transmission electron microscopy imaging. Here we can distinctly see that the interface, sharp interface is forming between the silicon and cobalt disilicide. To investigate the evolution of the distinct type of two cross-sectional nanowire, we have calculated the height from the surface level, depth from the surface level, and width at the surface level for the two distinct type of nanowires from the different size of cross-section from different TM images. And we have plotted mean of the height to width ratio with respect to the square root of the cross-sectional area of the nanowire, and we found that it is nearly constant 0.22 for the this type of nanowire, and the same goes to 0.23 for the flat top type of nanowire. We also plotted the depth and width ratio with respect to the square root of area of the cross section of the nanowire, and we found its mean value is 0.49, and for the flat top type of nanowire is 0.35 its mean value. So from this we can say that this supports that the nanowire shape is invariant. This is the atomic model where we just saw the two distinct type of facets. Here we have 111 interface, but in this case there is 111 silicon interface is matching with cobalt disilicide 115, and in this part silicon 115 is matching with cobalt disilicide 111. But for the flat top type of nanowire, we have in the both interface silicon 111 and cobalt disilicide 111 interface. After thoroughly investigating the growth of endotaxial cobalt disilicide nanowire on silicon 110 surfaces, I have carried out experiment to tune the dimension of the cobalt disilicide nanowire on silicon 110 surfaces. For that, I have changed the post-deposition annealing. For the first set of sample, I have annealed the sample for 10 minutes after the cobalt deposition, and for the second set of sample, I have annealed the sample for 40 minutes after the deposition of cobalt, and for the third set of sample, I have annealed the sample for 70 minutes after the deposition. Distinct type of morphology of the nanowire. So for the first set of sample, we observe from the ACM image there are nanowires on the surface separated from each other, and in between there are a lot of nanodots scattered on the surface. But for the 40-minute annual set of sample, there is no distinct nanodot present on the surface, but from this ACM image we can see that there are more number of nanowire present on the surface. And for the third set of sample, we observe the nanowire is more or less same, but it seems to be elongated. We have calculated the length with aspect ratio and plotted it, and we found that when we increase the annealing duration, the aspect ratio increases from 7.4 for the first set of sample to 12.6 for the 70-minute annealed sample. To look closely what happening, we have plotted the length and width with the area of the nanowire, and we find that indeed in the first set of samples there are a group of nano structure present which length and width is very same or close to same, and that means but there is a gap and the length and width are distributed. So there are two distinct types of nano structure. One is nanowire and other is nanodot, but for the second two set of sample there is only nanowire present. And here we have shown the aspect ratio variation with the annealing deviation, and also from the plot we have seen that the increase of the nanowire number density with the annealing time. This can be explained from the fact that with increasing the annealing duration, the nanodots which were present on the surface those agglomerate to form elongated and form a nanowire. And the nanowire width decreases, which increase the aspect ratio. This decrease of the nanowire width is supported by the fact that the material from the nanowire side will diffuses to the end of the nanowire along the length, and it increases its length and decreases its width by producing a more compact nanowire on the surface. We have also carried out tunneling spectroscopy measurement in the scanning tunneling spectroscopy, and we find that the nanowire tunneling spectroscopy is showing such a behavior with respect to the silicon surface. So, in summary, I have investigated the self-organized unidirectional nanowire formation by reactive physiotaxy. As the post-deposition and duration of the cobalt disilicide nanowire is increased, the nanowire aspect ratio is increased, forming a more compact nanowire. With the prolonged annealing, the nanowire width decreases, which lead to the increase of the nanowire aspect ratio. And with this method, we can fabricate well-ordered unidirectional nanowire for controlling the dimension of the nanowire. I would like to thank my supervisor, Professor Bhupendra Dev, Professor Andreas Hangleiter, and other collaborators for your kind attention. Please feel free to ask any question.